Thank you, Adam, for the invitation to present this work. And thank you for the warm welcome. Haven't actually done anything yet. So what I'd like to present is some work that we've been doing in a group at RMIT. It's a fairly large group. You see some of the people who are involved, and there's a number of others as well whose contribution to the work I'm presenting today was a little bit lower. So we're a group that is a mix of computer science and algorithm development, and artists and designers and the creative side of the world. Three things to sort of like to talk about. The first one is some work we're doing in generating aesthetically pleasing images from mathematical formulas. Second bit of work is taking perhaps a little bit more of a view of art that says if you're doing a drawing, you're going to do a series of strokes on paper, and if you can get the right kind of strokes, you can get some nice looking images. And the last thing is some new work from a bit of theory that we're just kind of developing and haven't quite figured out exactly what we can really do with it. Evolutionary art, evolution. If you think about evolution, what do you think of? Well, one thing is sort of a bit represented in this little graphic. It says that as time goes on and evolution does what it does, things get more complex. And certainly from the first single-cell organism to where we are now is a fair degree of increase of complexity. The other kind of notions that come to mind with evolution is this idea of survival of the fittest. The fittest get to breed and pass on their genes to the next generation. Things get more complex over time. Parents and children, no matter whether we're talking humans or animals or whatever, the idea is that genetic material gets transferred from parents to children. But actually, it doesn't just get copied from parents to children. It undergoes some change. So children get genetic material from both the parents, but then they don't get an exact copy of that because things get mutated and changed a bit. So there's those notions going on. And with evolution, there's always populations. There's the current population, and then there's the next generation and the generation after that. So these are the basic kind of ideas that are used in coming up with computer algorithms that simulate evolution. Evolutionary algorithms based on those notions. So if we're talking about computational evolution, we're really talking about solving some kind of a problem. And to solve in this method, we need to be able to have something that is a potential solution to the problem. So if our problem is to make a nice image, we have to be able to have a representation of images, and somehow one of them is going to be the solution. We need a way to rate every solution. So this is where the idea of fitness comes in. We need to be able to say for any potential solution, how good is it? And usually it's going to be some kind of a number, but as long as you can say that one solution is better than some other solution without actually giving it a number, still okay. And we need ways to make new solutions from existing ones. And in the evolutionary paradigm, we're going to be saying we'll take some parents, cross it, genetic material from the parents, cross it over, get the children, apply some mutation, and proceed through the generations in this way. Here's a couple of examples of some images that have come out of our system. Grey level and of course colour. Now, what's an image? Well, there's an image, and in essence an image is an array of dots. So a grey level image, we might say, is this array with each individual pixel with some value. And when we see it and perceive it, we recognise it as looking like something. So in a relatively simple image, the range of pixels is 0 to, it's actually 0 to 255, isn't it? Where the lower end is black and the higher end is white. Now, this kind of representation of an image is a little bit difficult to do anything with in the evolutionary world. But if we suppose we say an image is sort of a two-dimensional array, so if we go to mathematics a little bit, we could say, well, an image in fact is some function of x and y. So if we could come up with a function and evaluate it in some range, and each of those evaluations is a pixel value, then we're going to have an image. The example here, suppose we say that the function we're going to evaluate is x plus y, and for convenience, and you'll see why it's convenient I think in a second, we'll just assume we've got an image that is this 128 by 128. So we're going to take this image x plus y and evaluate from x equals 0, or, well, let's say x equals 1 to 128, same thing for y. What's this image going to look like? It's going to look exactly like this, because we're evaluating x plus y. Well, down in this area where x is small and y is small, x plus y will be small, and 0 is black, so this area is going to be black. And I've conveniently only gone this high, 128, 128, 256, so that's the white. And you can see that this area is sort of mostly white, and as you might expect, there's a systematic gradient going from here up to here. So this gives us a basic mechanism for having an image, or having a formula and getting an image from it. What if this our function was a bit more complex. So if our function looked like this, so we've still got just x and y, one of these images, and I can't remember which one, comes from this formula. So there's a little bit of fine print here, of course. We have to decide what range to choose from x and y, and we have to make sure that if we're evaluating arbitrary formulas, the result of the evaluation somehow ends up in the proper range of pixels, 0 to 255. And all of that's sort of quite doable. So in the system here, we're going to say an image is going to be represented by a formula in x and y. The next thing we needed was to be able to take take parents and make children. Well, here's a parent. See that formula in x and y. And here's another parent. To get the children, what we're going to do is just take an arbitrary point here. Not exactly an arbitrary point in the text, but we're only going to break it up at meaningful points. So here we're saying at this point here, we're going to take the first bit of this parent, this amount of genetic material, and that's going to be the first bit of this child. And from the second parent, we're going to take this bit of genetic material and attach it to this child. And together, that's given us the first of the children. And the leftover bits make the second child. Mutation is kind of pretty straightforward. We're just going to say we'll take a piece of this one and throw it away and randomly generate a new piece of the formula, and here's the new child. So you can see that seems reasonably straightforward. As long as we don't cut a formula in a silly place like this or like this, we can guarantee that the children are going to be proper formulas. And part of the underlying mechanism here is that we always need to be able to, at any time, generate a random formula. Fitness. How do we get the fitness? Because that's a key aspect in trying to improve. Well, for this work, we take the formula, convert it into an image, and ask the user to look at it, and ask the user to rank them. Which ones do they like? Which ones do they like best? So here's the overall algorithm for this part of the work. We need a population of things, so to start off with, the first population gets made at random. We have a population of 8, mostly because that's a reasonably convenient number of images to show to a user and have them make some kind of judgment about it. Ranking of each individual is the fitness, and then we can get the next generation. So we want to select the parents, and somewhat like biological evolution, it's a bit random, but if you fit it, you get more chance to reproduce. Crossover and mutation we've described, and mutation, and then that gives us the next generation, and show it to the user and keep going. So anybody who's a programmer will immediately see a bit of a problem with my algorithm. There's no way to stop. You have to keep going forever and ever and ever. In practice, you stop when you get sick of it. So, here's a couple of screenshots from running the program, this particular program. And this is the first generation. So, you can see that here and here, for example, the image that got made at random is so bad that it can't even be drawn. There's a fair number of images that are, like these ones here, that are just not interesting at all. And if you do stuff at random, you can't be surprised if some things are just not interesting. But there's a couple there that are showing a little bit of structure, showing something that's interesting. So by good luck, in the first generation, we've kind of found something that we want to pursue. So we might say we like 1 and 2, or maybe 1, 2 and 3, and present that to the algorithm to go to the next generation. And if we go here, I've got to the 4th generation, and you can sort of see that something is developing a little bit. There's still a fair bit of junk floating around, but generally there's always going to be some junk, because we did, even with good parents, do random things to it. You're likely to end up with something that's not very interesting. But these here and this last one here, it's visually starting to look quite okay. And you can start to see the development of a bit of a family here, because this guy here is sort of looking pretty similar to this one, but with a bit of variation. So here's some examples of images that somebody got, one of our collaborators, just by pursuing the basic evolutionary loop. By chance, a red and black image arrived, and with the user continually selecting, saying, I like red and black, I like red and black, I like red and black, these various kinds of renderings came out. Here's 4 more examples from another run, and you can sort of see that there's sort of a family resemblance going on here. So this one was a bit of a coming out in a fairly early generation, and you can see that this one is kind of a more complex, more embellished view of this one, and kind of so is this. And with going through the system and pursuing on and on, you see how the families of images come out, and then all of a sudden you'll get one whole new image that you never saw before, and variations of it start coming out. So here's a little bit of the underneath, and it's all perhaps a little bit technical, but you can see here that there's causes in here, and pi is in here, and there's multiplication and division. And so this, evaluating this formula, gives grey image. For colour images, what we do is say we need one formula for red, one formula for green, and one formula for blue. And when we evaluate the formula, we get RGB, which is what gets in the final result. So a couple of our collaborating artists noticed these images that evolved, composed them together manually to make this one, and it did fairly well at an evolved art competition with it. So that's a way of getting sort of images, nice looking images from formulas. The next part of the thing I'd like to talk about is an alternative way to get images. In this kind of model of an image, what we're saying is that the way you make an image is you put strokes on a canvas. And what we're going to do is evolve a program that puts strokes on a canvas. The kind of strokes we've done a fair bit of work with is lines and triangles, but also other kinds of strokes as well. So if you think of perhaps something like a pencil sketch, you're drawing a line with a pencil, and if we want to draw one straight line, we have to say, it's going at this X and Y position on the canvas, it's going to be this long, the angle to the X direction will be this much, and the grey level intensity will be this much. So if we can put lots of lines in all the right places, that's going to make a picture. So here's an example of a picture with lines, enough lines in the right places to make an image. And here's a picture with that's using coloured pencils, that's put enough lines in the right places to make an interesting looking image. So the evolutionary mechanism under all this is that we need to represent these programs that draw lots of strokes, and a way for the programs to get the right number of strokes and the right X, Y length, whatever parameter values. So we're using our genetic programming formulation here. So to get these draws, 1, 2, 3, 4, 5 draw strokes is represented here. That's done by a program, a higher level program that can do two things. So it's going to do 2 draws. Same with this one. And this one is doing a single draw. And the program 3 can do 3 things. It can take, first it'll do this, and then do this, and then do this. So it's a fairly typical kind of a recursive structure you might see in program development. So we've seen that if we're working with evolution, with genetic programming, we need to have this population of programs, and we've had a look at what one program looks like. We need crossover and mutation operators, and we need to have fitness. Well, crossovers fairly straightforward. If we have this program and this program, we can say, all right, randomly we'll pick a point in here, say this one, and randomly pick a point here, and then just move this into here, and this over here, and we've got 2 children from 2 parents. The thing to keep in mind here is that because of this kind of representation, large chunks of the drawing can go from parent to child. Because if we pick this position here as a crossover point, potentially there's 100 strokes being drawn under here. So all of these strokes will go to the child. So the hope is that if we've got a good chunk of a tree here, then it can go to a child, and the child can be even better because we've got some other good bits as well. Mutations, pretty straightforward. So we'll pick this node here, for example, delete this whole tree under it, and then randomly construct a new program to go in this position here. The fitness. Fitness. As perhaps you might have guessed from my examples, the artist provides a target image, and the fitness is driven by differences between the current individual and the target image. We're using a straight pixel by pixel differences between the evolved image and the target image. So we've got the target here, the evolved image is here, 1 pixel at a time, see how different they are. Add up the differences. If the difference between the evolved image and the target is small, then that means this program's got a good fitness. One of the things that we kind of noticed early on is that by looking at the evolutionary process, you could see that each generation, the best individual sort of gets better and better. So we thought, why don't we just take the best individual and of each generation and run them together into a movie, into an animation. with some modifications of the fine detail of that process. That's what we've done. And a lot of our animations are done in this fashion. Should come. And this is where it gets very embarrassing. Because on my computer, it's all happening. And here, nothing is happening.
Full screen on your computer?
Open up another program.
Yeah, open it up in Windows Media Player. Is that VLC using?
That's VLC.
Maybe it's the frame rate. Is there a way you can slow it down?
There's some setting here of
Video.
overlay something or other. De-interlace maybe.
Try view full screen.
I don't think it's going to help with full screen, but we'll have a look.
It could be the frame rate. Is it at a high frame rate in this?
No, it's a pretty regular frame rate.
Do you want to open it up in Windows Media Player, like right click the file and open?
Let's stop this.
Faster.
Same problem.
Faster. No, it's much faster. It's really
Go to desktop. Set up an alternate knowledge on the desktop.
It's training here, but not there. Oh, there's one that plays. How about that? That's one from a little bit further on. But maybe we can do it like this. So here's the one I was looking for first before. So it starts. So,
There you go.
Up there.
Big full screen.
well, all right. I think it's better this way, though.
Uh-huh.
Middle one. Top middle, next to the X. Yes.
So, when it started off, it was just a whole lot of random lines, just like perhaps the primordial swamp of early evolution. And then as the animation that evolution proceeds, slowly the subject emerges from the randomness. The way we do most of our videos is to go from random to the most photorealism, the best naturally we're going to show, and then go back to random. Let's go. I don't believe I killed the PowerPoint, but it seems to have gone. I did kill it.
Oh, that's where.
I think it's just a quick little arrow down the bottom there. It should bring up all your other tabs.
Yeah.
Down here.
Yep.
I actually saw it closer.
Okay, so
Singularity, a copy of Singularity.
Okay, so that was sort of the using the kind of the raw kind of result from using a basic kind of a pencil stroke. The next example is one that open with. So this one was done by somebody whose primary interest was in art and assembling pieces themselves. So the individual pieces of the picture were done by the evolutionary process, and then he manually assembled the pieces into the full video. we saw this one already. So the idea of this one is that the strokes we're making are no longer lines, they're curved strokes, and the underlying model of the strokes is a spline, and the Bezier spline, and the task is to try and evolve no, I lied. So here we're the previous one we saw just did black splines on top to get the picture. This one was doing black and white splines together to get the final result. Another one that was done by somebody whose primary interest is from the art side, and the individual ballerina poses were evolved using the evolutionary art program, and then the individual bits were composed into the final piece. Lovely little piece that I really like, that has nicely captured the mood of the gentleness of ballet and the way the animations come and go. Back to the pencil sketch.
Can you tell us again how the target is actually determined? I don't quite see how the target is.
The artist provides the target.
Yeah, but how does it interact with the computation then?
With the evolutionary setup makes a program that draws an image, and then that image that's drawn is compared to the target, and the targets, we know exactly what it is because that's what the artist gave us. And
Okay.
direct comparison, how close are the pixels in each position
Okay.
to each other?
Okay. So the target itself never directly goes into the program.
No.
Okay.
No, no.
So you just manipulate the formula.
Well, this is a little different. The formulae was for the first part, that was the other images. Here there are no formulas, but there's individual strokes. And this one is actually a bit different to the previous ones because here the strokes are individual little tiles, and the placement is such that every tile has to go into a grid position and there's not allowed to be empty space anywhere. But there's still a basic idea of doing strokes. And I'm not sure if anybody's noticed what these individual tiles are. Cigarettes, yes. So the artist in coming up with this piece has found I think a nice, elegant way to send the message.
So this is your version of plain packaging. Just change it to brownie green, you'll be right.
So I'll just show. Here's another one I quite like, which has I think managed to capture the spirit of the medium in giving the message. I think that with making these kinds of mosaics, the challenge to the artist is to come up with the message that's based on the semantics of the individual tiles compared to the final overall image.
So typically, how many evaluations are actually done to get these results? Thousands? Tens of thousands?
It does depend on the complexity and size and so on. Generally, we're talking about 10,000 evaluations to 50,000. Typical number.
There's a fair amount of human effort involved.
Well, there's not a lot of human effort in these ones because to get the fitness of these ones, that's done computationally because you've got the target to do the comparisons. It's those first ones where each one has to be looked at is where the human fatigue it comes in. And I'll just have a look at So this is a compilation of things from that last method that I mentioned earlier. So I think we're able to get visually interesting little animation sequences from this method. The results are kind of still in the sphere of the abstract, and they perhaps need a little bit more realism in order to make them a bit more interesting to viewers. I'm not real sure. I'll just show one more and then wrap up. Interested to know if anybody could figure out where that came from by only ever having seen what's there.
Is it a wine glass?
And something's happening to the wine glass. A bit of wine got tipped into it.
Yeah.
So just a couple of things to finish up. One of the things that sort of surprised me at the time, but in retrospect it's not really a surprise, the artists we were working with weren't that interested in the program that evolves those images, the first thing that I talked about. And the reason that they weren't that interested is there was very little opportunity for them to provide any kind of creative input. All they could do was say, I like that and I don't like that. And they wanted to have much more creative input.
And did they corrupt the image or enhance it?
Sorry?
Did they corrupt the image or enhance it?
With those first ones, they couldn't really do anything because there's no way to do it. With the second, the animations from the stroke-based method, they had some, in working with the program that does those things, they had a lot of choice about how many, what kind of target to use, what kind of strokes to use, whether to use a lot of strokes or a few strokes, whether to use short ones or long ones, whether to use sort of triangles or lines or some other form. So they were much happier to work with that. But still, even then, they wanted to use that those programs to make the building blocks of something that they then composed with the other tools that they're familiar with, like video editing programs, and put in fading and fade out and all of those sort of things.
And was the methodology scientific? Did they use the scientific method, or was it just some artistic inspiration?
So the question is, did they use some kind of scientific method?
In order to experiment to see what they were after, or did they just go after some sort of artistic?
I think we were kind of providing the scientific method, and the artists weren't that interested in that. They just wanted to be able to do things that that they liked, the outcomes they liked. A big question that always comes up is it art? And what's art anyway? So we'll ignore that question. The thing that's most interesting to me is this idea of aesthetic judgment. At the moment, in our work and pretty much any other evolutionary art work that's going on anywhere in the world, the aesthetic judgment, is it a nice picture, is it a nice video, is in some way being provided by a person, by a human. The holy grail of this field is, can this aesthetic judgment be done computationally? And that's an unanswered question. We've got a couple of ideas on how we might make a little bit of progress that we're currently pursuing. If you'd like to see a few more things, there's some more examples on this website. And if you can't remember the website, you can, if you Google RMIT Evolutionary Art, find it. If you want to try something like this yourself, we have an iPhone and iPad app that's based on some of the underlying algorithms. And if you want to try some things yourself, you can just get it and download it. I have to say that the things that people have done on the iPad look really terrific. The iPhone itself seems just a little bit too small to get anything that is visually stunning. But the iPad is big enough and resolution is good enough to get quite stunning results. Be happy to answer any questions if anybody's got any more.
In the first part you showed we had geometric formulas.
Yep.
Your method of doing the crossovers of an arbitrary point, it struck me that that was fairly arbitrary itself. And the question I would like to ask is, generally with the evolutionary program, one hopes that in addition to finding some good examples in each generation, one would hope that the average quality would improve. I have a feeling your average quality would not improve.
Well, that's kind of
I'd be interested in that.
an interesting
Yeah, because you
point.
usually want the average quality to improve as well, because if it doesn't, you may as well just keep being random and not evolutionary.
But at the same time, if your average fitness is improving, it means probably that the individuals are getting more and more the same, so that you're losing diversity, so that the opportunity to come up with something that's good but different is getting smaller and smaller.
It may not be. Yeah, it's a moot question, but it's interesting. If it kept improving, then in effect you've got a secondary saying, hey, this is a good thing to do.
I'm in favour of continuing the questioning, but for those who want to have half an hour break, that started a couple of minutes ago, so we have to get back here at 5 for Marcus's talk too. Okay? So keep questioning if you're happy with that.
Sure.
Is there any more questions? Right.
In that, again, coming back, instead of the formulaic approach, you could have started with zero generation of images and regarded the entire image as the chromosome.
Just in the raw pixel
The
format.
whole image, and therefore you could have created slices of permutations and slices of cross talk from the imagery directly without the geometric. Because when you've chosen the geometric, the tendency, of course, to result is always geometric.
Well, that's right.
Whereas if you did it from the pure image, you may have a greater variety of results.
Yeah, the choice of representation is always going to bias the kinds of things that come out. But if you just stick with raw pixels, I don't think there's going to be enough structure or enough sort of kind of a model of what's happening to be guided towards something good. I think you're probably just going to stumble around in random collections of pixels that stay random but don't sort of improve too much.
It's like a painter's palette that always turns grey in the end.
Yeah.